This is John Black, Super Chemist, and this is a video from a playlist called New and Updated Time and Time Dilation. This is part 7. This individual video is about the twin paradox and does direction matter when it comes to time dilation. I'm going to assume that you know what a photon clock is. This is red line means you're just standing still. That's the smallest distance in between your plates of your photon clock. If you move, you can see you throw out a photon, it has to go up. The plate is going to move over to here or move over to here depending on your direction. And the line will get longer. This line, this red line, if it is the shortest distance you can have, then any direction you move in, it will elongate the line and stretch out a second. This configuration, going straight up and down here, is true standing still. True. It is the only time you are not direction dependent when it comes to time dilation. And remember, when you are accelerating your time dilation. When you are at constant velocity, your time dilation is constant. Meaning, during acceleration, you can see the line grows. See how it gets bigger and bigger and bigger? Then here, the line stays the same because you turned your rockets off and you're just constant velocity. You keep the same time dilated second, but it stays constant because you're going at a constant velocity. Here, you're not going at a constant velocity. You're changing your velocity more and more and more so that the line gets bigger. So once you make this line bigger, that second, you are direction dependent on your time dilation. Because if you start going to the left, you're going to make the line smaller. And if you keep continuing going to the right, you're going to make the line bigger. Then you keep floating and floating and floating, and sooner or later around here, you're going to put on your rockets so that you can slow down. You're going to accelerate the opposite direction. And what happens when you accelerate in this direction? Look, your thing gets smaller and smaller and smaller because you are direction dependent at this point. This is your second. So if this line gets smaller, that means the duration of your second is smaller. Here you're stretching a second out so it lasts longer. Here you're doing the opposite. You keep deaccelerating until you go back to your original configuration or original line length of a second. Notice when you stand still again, either way you go, you're going to make this line bigger. And that time dilates you. You go this way, it's time dilated. You go this way, it's time dilated. But this only happens when you have a true standing still clock. Set up here, which was standing still, and then come back. You put your rockets on, and now look, the line gets bigger, 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 until you turn your rockets off and you're at constant velocity. Then you turn your rockets back on in the opposite direction so that you can slow down. And look, your line gets smaller and smaller and smaller until you get back home and your clock is at a standing still, smallest distance here that you can be. I want you to realize a couple things. One, this red line and this blue line, they are not you. You know, it's not you going through, because you got this orange line here, right here. That's not you going through space and you going through time. And then you have to get this resultant vector, you know. No. It is the photon. The photon has to go up and down, or the information carrier has to go up and down when you stand still. But when you move, it has a y vector, component vector. But now, if you move, it has to keep up with you. So now it has a x spatial. They're both spatial, and then you get the resultant vector of that photon. It's not you. It's the photon, and you get its, because it's stretching out that distance for a second to happen. The second thing I need you to understand is standing still and relative standing still are two different things. This is standing still. This on Earth, this is relative standing still when we pretend that we have a red line like that. We don't have a red line, we have a blue line. And you can see we're only moving like, what, 1 million miles an hour, you know, through space, our galaxy. So that's nothing. You can barely tell the difference between this and this. But there is a difference. When it comes to time dilation, this is not direction dependent. This for Earth, because it's really like this is overpronounced, is direction dependent. And you can barely see here the blue line on top, so I did it down here. And then I even did it even more pronounced so you can see it. And this is what we're going to use because you can't see this stuff. So this is standing still on Earth. Really, it's like this, but we can't see that line. So I did it like this. I want you to think about it. when you were here in your constant velocity, no rockets, you could have said, oh, if you, let's say I knocked you out and you're on Earth, put you in this ship, and then you're going constant velocity. You wake up, you don't know, you think you're standing still because you're floating. So you use this clock. But you can see if your clock is really like this because you were standing still here. Now you're not. You stretched out the second. So if you move to the right, you grow the line. You make it bigger because you have this type of clock where it's stretched out in the right direction. So if you start going more into the right direction, you're going to grow it even more. And if you turn it this way, you will shrink the line. You will make the line get smaller. You make the plates get closer together. And the smaller the line is, the faster time moves. But what about up here? Up here, you are standing still for real. This is pretend. This is relative standing still. This is real standing still, okay, relative to space-time. And you can see any direction you move, because this is the smallest distance. If you move, if this is smallest, you're going to have a bigger. Either way, no matter what direction you go, you're going to make it bigger, just like here. That's why this works out the way they say, because they are using a true standing still clock. But we do not have a true standing still clock. We have a relative standing still clock. So when you're, let's say this is Earth. If you move this way, yeah, it depends on where is your clock. Is it like this? If it's like this. So now that we know these two things, let's go to the relative standing still. Now this was when you were just floating in space. You were not. This was not Earth, and this was not Earth. Okay, this is Earth, and as you can see, the red line isn't really vertical. It's like this, but we have it more pronounced. So we start out here on Earth with this clock here that is not standing still, and we're going to pretend that the galaxy is moving in the X direction. So the planets that we're at and we're going to are also moving in the same direction, and we are in the same direction. We all have the same momentum, right? So that's why we have this clock. So if you're going this way, you can see the thing would be stretched out in this direction. If you were going in the opposite direction like that, it would be stretched out this way. See, when you go back home, look, it stretches out this way. When you go to this planet, it stretches out that way. They're opposite. So we have a clock like this. So when we start accelerating, like up here, our line gets bigger and bigger and bigger. Then we go to constant velocity. The line stays constant. Then we deaccelerate, and we get the line smaller and smaller and smaller. And then we go back to our original position, because this is going the same speed as this way, going from left to right. And therefore, when we get to this standing, this is true standing still, but we are at relative standing still. So when we get to the next planet, we're going to have the same exact line. Like up here, they have the same exact line. We will have the same time dilated. We will have the same exact thing right here. So everything lines up, though, between these two scenarios. You get the line gets bigger the entire time. See, notice how this line gets bigger the whole time. Then you stop and turn around, and look, the line gets bigger the whole time. You're going to get time dilated both directions. Here, I agree. You can see the line gets bigger and bigger and bigger. Even though it's getting smaller, when you slow down, it's never smaller than the original configuration. Just like here, the line is never smaller than this line, this configuration here. Never, even when you're slowing down. So that means you're always being time dilated. But what about when you turn around and come back, just like this here right here? Yeah, your velocity is going left to right. You have this type of clock. So when you go back, when you put your thrusters on to go back, what's going to happen? It's not going to be like up here where you're making the line bigger this way. No, you're making the line smaller. You're making the plates, just like if you stopped right here and started going back. Look at the plates. They get closer and closer together. Just like here, the plates are going to get closer. They're going to be so close here that you don't even need two lines. And you get slower and slower and slower, and then you're at constant velocity, and then you accelerate in the other direction. And what happens when you go in the other direction? Look, your line gets bigger and bigger and bigger. See, because it's direction dependent. It gets bigger and bigger until you get your original configuration. Just like up here, you get your original configuration. But your original configuration is not standing still true. It's standing still relative. But I want you to notice, when you went back over here, the line always grew, or it got smaller, but it was always bigger than your original configurations. Always. Look here. The line is not getting bigger when you go back. The line is getting smaller and smaller and smaller. And then, yes, it does get bigger here, but it never, ever, ever. This line right here, and this line here, and this line here, they will never be as big or bigger than these, these stopped relative standing still lines. So this entire time you're being time dilated in the opposite direction as this. So what happens when you go, if the galaxy was moving like this, left to right, and we started going from this planet to this planet, this is what would happen. You go to the next planet, and you would get time dilated just like they tell you. But on the way back, you will get time dilated in the opposite direction. And that line will get smaller and smaller, speeding up time. And this time dilation and this time dilation are equal, but opposite. So what does that mean? That means, yes, you get to that other planet, you're going to be younger than the person on this planet here at Earth. But when you come back, you'll be time dilated in the opposite direction, and now this person will catch up. They'll even out when you're done. On the way back, the Earth man, he will be aging slower than the spaceship man, because look at his line. His line is this right here. And look, your line is smaller. You're in the spaceship. So your time is moving fast. The Earth time is moving slow. Most likely the galaxy is moving in a diagonal, path. But let's pretend that it's going perpendicular to the plane and it's going in the y-axis. What do? Okay, first of all, up here I said it wasn't you going through time and space. It was the photon going through x and y. Here we're going to have to do u. Okay, you are going this way and you're going this way because the galaxy is moving that way. You're actually moving this way. I got you going faster than your ship than you are in your galaxy, so the line is more horizontal, and this is your new direction and your speed. We rotate our photon clock so that it is parallel. See all these dotted orange lines? They're all parallel. Now we know your direction. This is your direction and your speed, and we have a photon clock going back and forth. We're just basically doing what we did up here. We got the photon, two component vectors, x and y, in the spatial dimensions, and then we find the resultant. And that resultant relative to this tells us our gamma. So you will get time dilation for going through the galaxy, but you also get time dilation in the x direction. This tells your total time dilation, your new second. But I want you to notice over here, this is you going up, right, with the galaxy. Whether you move in the x direction this way or you move in the x direction this way, you still get the same time dilation either way. So when you go to this next planet, you're going to slow down and you're going to go back to this vertical velocity here. And what happens when you're at this? You go back to this. No matter which direction you go, you're going to elongate the line. So in this scenario, when you come back, you will be time dilated again. So if the galaxy is going totally in the y direction, when we come back, we will get time dilated, and when we go there, we'll get time dilated. We'll get time dilated both ways. So we will be younger when we come back to Earth. So the first scenario, the man was standing still relative to space-time. He was time dilated both directions. He's younger when he comes back. If you're talking about Earth, where you're in a galaxy and the galaxy is moving in the x-axis, same plane as the galaxy, then you will get time dilation going to the one star going to one way, but when you come back, you'll get the opposite. And when you return, you will be the same age. And if you go in the other direction that the galaxy is going in, then you would do this. You would get your time sped up, and then when you come back, it would be sped down, and they would cancel each other out, and you would be the same age. If the galaxy is going in the y direction, you will get time dilated when you go to the next planet, and you will get time dilated when you get back, just like this. The only difference is this will give you less time dilation. If you figured out the math, this right here, you get more time dilation because you're moving through the y and the x. This, you're only moving through the x.